Um, I feel a little bit out of bounds since I'm not actually a paid security person official with a business card or anything. I'm actually more of a phone guy, so I've just kind of done phones for about 7, 8 years now. Usually voice over IP, but the latest place I'm working at is all software-defined radios and GSM networks. So there's a lot of security to teach about in that, and that's what I do for the company. I do a lot of traveling and teaching for how secure GSM is, how secure certain applications are if you're using an SDR in that environment, or if you have a radio-enabled application, how secure it can be. So, and I do program. That's 90% of the time. That's developing things and making things easier. But I am not a security guy. I'm a phone guy. But we get to mess with software-defined radios, which was really nice. For the last 5 years before this, I was just working on PBXs. Is this the audio all right, or is it buzzy? Oh, okay. So instead of cables and IP packets, I was exposed for the first time to radio frequency, and what a nightmare this can be, and how it's like black magic if you actually have someone that works for your company that understands RF at a very deep level. They'll explain things to you, why it works and why it doesn't work, and none of those really would set off anything in your mind that does actually explain why it does or does not work. So you just leave them well enough alone in the corner of the lab, and they do their RF things and try their best to explain to the mere mortals what RF actually is. So I'll do my best. The recent change with all this is these software-defined radios are now a consumer device. They were exclusively for the military and intelligence communities for about 20 years, and before that they were somebody's academic dream of what you could do if you replaced all this hardware, this pesky hardware that's locked into place and locked into a certain functionality. If you could just pipe raw waveforms into a computer and have the computer do all the digital signal processing and demodulate and interpret this data. So now software is eating everything, as was so famously quoted, and we have what begins to look like a completely generic radio. Everything that encodes or decodes the signals is in software. So you don't have any FPGAs. You may have some optimizing FPGAs, but for the most part, you're getting raw waveforms over USB or Ethernet, and then you're writing all the code, all the user space code that turns those into bit streams and corrects errors and everything. So you're really responsible for everything, from correctly in interpreting what kind of signal is coming in and how it should be framed out, how it should be turned into something that the program can actually manipulate. In a lot of the software that we write, we use something called soft vectors. So it's not a 1 or a 0. It looks like a 1. We think it's a 1. And so we have these like fuzzy streams of bits. We call them soft vectors. These radios are now differentiated by sensitivity, their frequency response range, and then the megasamples that you can listen to, I guess, at the same time. So this is one that we actually put in base stations. These are going cellular base stations, and we don't sell them separately. But this has a really narrow response range. It's 850 to 1900 because those are the bands of GSM, so we don't really care about anything else. It's also fine-tuned to really demodulate that signal cleanly there without a lot of extra effort. There's some optimizations in the FPGA so that the hardware doesn't have to do such heavy lifting. There's this guy that just came out after a really successful Kickstarter. It's a Blade RF. These are cheap at only $450. And that is cheap when you compare it to the whatever industry standard Edis N210. These are about $1,700. And they have a 310 that came out that's $4,000. But this, you get to change, the little asterisk there is, you get to change this daughter board for whichever frequency you actually want to listen to. So for me, it's 400 to 4400. Those are the cellular frequencies. But if you wanted to listen to 6 gigahertz, you can. or really fine-tuned between 5 and 6 gigahertz, you can. You can buy different daughter boards for these. And these are really nice because they use Ethernet instead of USB. So you have a lot wider megasample bandwidth. But for only 25 bucks, if you search for something called RTL SDR, you can do stuff like this and get like fast Fourier transform or waterfall diagram of energy coming in at different frequencies. You can even activate different filters and demodulate CB radio, FM radio, AM radio, things like that. So you can get started for less than 50 bucks, maybe an external antenna. So what does this all really mean? Wahoo, we have radios. Did anybody go war driving when war driving first became a thing? Does anyone not know what war driving is because everyone has an iPad and doesn't need to know how anything works anymore? When war driving first became a thing, it was, you could enable promiscuous mode on your wireless card, and you could just listen to samples coming in, being demodulated, turned into beacons and some traffic, and you could see it all. But that was for a very specific frequency range and a very specific application. Well, now you can just kind of listen to everything that's out there and see what's happening. This is a screenshot of an amateur radio competition going on in a building. So these are short little bursts at different frequencies and energy levels. And you can, if you know what is being sent and how it's being sent, you can demodulate it and interpret it and do other things with it. You can also respond to it if you understand how the protocol works. So what types of things? Anything with a radio. Remote entry systems, they have radios. Sensor data coming from field equipment, or I don't know, your Nest thermostat maybe gives off something. I don't know. Anything with a sensor in it, and I'm sure they're all around. Audio equipment, also very fun. At a conference, somebody had an SDR and was broadcasting at the wrong frequency and nobody could hear the speaker. Super fun. Restaurant table buzzers. I'm waiting for the person that writes the Python code that sends out your table is ready notifications to every single, little thing at Outback Steakhouse, and they all just start buzzing, or Cheesecake Factory, those little hockey pucks that they give you. Stuff like that. Stuff that was never designed to actually be secure because you wouldn't have access to the medium. So with Wi-Fi, we could actually use one of these to demodulate Wi-Fi and look into the protocol and all that, but we already have specialized equipment for it. Wi-Fi cards, wireless cards. They already do a great job of it. What we're talking about is things that didn't exactly make it into the consumer's hands. The media access layer that isn't available on the internet, and you don't really know how it works, but now you can listen to it and you can talk to it if you send it the right waveforms. And if you can, gather samples, you can probably crowdsource a solution as to how to talk to these things. Just a few things out there that maybe did have security in mind, and others that maybe did not have security in mind. They're generically deployed and averse to upgrades. Something that's already out there, you're probably not going to be able to upgrade it. If you do, it means a complete firmware reflash. Maybe that's too dangerous. You'd rather just accept the security risk, or it's completely baked into the product. You'd have to replace the unit entirely. It was never intended to be an upgradable system. It was also never intended to be able to be talked to. So this could have happened in the past. Could have happened, properly motivated. Nation states have, of course, reverse engineered these things with hardware and built dedicated systems to speak to other people's devices that did not want to be spoken to. But now this is the difference of going from punch card programming to Python interpreter in your browser. You can just try stuff out. You can record samples and you can just try to demodulate it. You can try to talk to it. You can try to interact with it. And you don't have to, rewrite a bill of materials and have Foxconn build another, demo board for you. So super dangerous. So what is one big system that's out there in the world that is averse to upgrades? Probably like the entire cellular network. It was invented in the late 70s, 80s, and deployed into the 90s, and now it's worldwide. It's everywhere, I guess, except I-90, which is CDMA because Qualcomm is a really good patent litigator. But anyway, GSM is basically everywhere else except for large rural regions. And it's kind of locked into a standard. You can't exactly upgrade it because all the handsets are already out. So if you added a bunch of features to it, you'd have to upgrade all the handsets. So it's impossible to upgrade. And it was also designed with implicit trust of the network because it was never thought possible that somebody would be able to launch a virtual machine on a laptop, plug a USB cable into something like this, give it 12 volts of DC, and be a cellular network. The original base stations were entire racks of systems and non-portable at all. They started getting smaller and smaller and smaller, and now they're down to actually a C++ program that is, 8 megabytes compiled and an atom board worth of power. So that's pretty creepy. A whole bunch of attacks become possible. It's basically ISDN over radio, if you know what ISDN is. The guys who invented ISDN basically went back to the drawing board and said, well, how do we do this over radio? So a lot of the standards are even they're called LDAP instead of, or LAPD, not LDAP, LAPD. Instead of LAPD, it's LAPD sub M for mobile. And there's little asterisks all over the documentation that says, well, this entire last chapter doesn't apply. Just by the way, this does not apply if you're using it over a radio. So a real hack job on some of the definitions. Couple of units of currency we'll talk about. Bursts, frames, and channels. Bursts are the tiniest thing you can send out. They're like 100 bits, and they're in certain configurations. You send many of them out in a certain sequence, and you get frames, and those frames constitute channels. Going back to this, it's FDMA and TDMA at the same time. So wireless networks are TDMA. Everyone waits for their time division. And frequency division is the method GSM uses to separate the uplink and downlink. So you can have bidirectional communication on uplink and downlink on different frequencies, and it's also time hopping on time slots at the same time. There's a few different types of channels. These are all the channels that fit with that font on that slide. They are broken down into a couple different types. There's broadcast channels and dedicated channels. There's also there's a whole bunch of other channels. But in the broadcast channels, you have things like frequency correction and time sync. The handset makes its best guess as to what the frequency of the network is. It tries to grab it, but the network also constantly sends this information down to the handset and says, oh, this is the exact frequency that I'm on. This is the exact frequency that I'm on. And if you skew that over time, you can actually break handsets. If you skew it over a period of time so that it's outside the window of error, it's like the classic frog in boiling water thing. It moves out of the workable frequency range, and then if you shut off your base station, it tries to connect to another network. It's completely outside of the range of acceptable frequencies, and the handset won't work until you power cycle it. So fun things like that. There's a bunch of network meta information just floating through the air. These are all broadcast. They're not encrypted at all. You can just look at them if you can demodulate them. And you see paging requests for handsets. And then once you actually get a page and a response, now we're talking about dedicated channels. So dedicated channels for individual handsets are negotiated via broadcast. Really. If you've dealt with voice over IP, it's the same type of thing. They have separate signaling and media channels in dedicated channels. So, okay, this is a lot of channels and bursts and things and whatever. What does this look like? It kind of looks like this. So this is the downlink, and down here is, find the cursor. Down here is the uplink. So these are two different frequencies. They're like 45 megahertz offset, and they're going at the same time. One is going down to the phone, one's coming from the phone to the network. So we'll just talk about the downlink because it's 215. Along the left-hand side, those are time slots. You have 8 time slots, and you can assign different purposes for each time slot. So these, with these TCH values, time slot 2 through 7, those are voice channels. They're for dedicated audio channels or GPRS channels. And all these up here, this line, these SDCCH, these are signaling channels. So they're either sending text messages to each other, they're handling registration traffic, they're doing data-like things, but not GPRS. And the very top one is the beacon. This is the magic time slot 0, ARFCAN 0, whatever. It's called the beacon. It handles all of everything else. It handles frequency correction, scheduling. The beacon, actual meta information is in there as to the ID of the network. And then the interesting things are CCCH and RATCH on the other side. These two. These are the things that you listen to see who is being paged by the network or who is paging the network. So these are the page and response channels. It's common control channel and random access. This random access burst channel. So, go back to the slides. If I can find my pointer. There we go. That's what you can passively monitor. Those are all the broadcasts going on that you can passively monitor. Once they get into a dedicated voice channel, it can be encrypted. You can't monitor it. So what's interesting? These exchanges. Who is being paged by whom, and if it responds, if it's on the network or not. So you can see which handsets are in a given area just by listening to it. If you can monitor SDCCH, if it's not encrypted, you can see text messages flying back and forth. They're just encoded in a GSM standard encoding, so you can just decode them and look at them. How do we mitigate all that? Well, you can obfuscate. So does anyone know what an IMSI is? I'm just wondering if IMSI catching has ever made its way here. Yes, okay. So IMSI is like your thumbprint in the phone. If you take the SIM card out of a GSM phone, the IMSI is your customer number, is your unique identity on the network. If somebody clones, oh, that's a different topic. Whatever. Your IMSI is your unique ID. They can tie it back to you as a person, as an account holder. So it's very sensitive information. So what usually happens, the first exchange with the network is, I'd like to register you to your network. That's great. Here's my IMSI. Give me a temporary mobile subscriber ID. The other one is the international mobile subscriber ID. Give me a temporary one. So it gives you hex 10. And then next time it gives you a totally random number, and you keep exchanging these numbers. So the only way to trace back some activity to an IMSI is to find all the TIMSI and IMSI exchanges along that whole way, all the way back to the original exchange. So it's pretty hard to do. Also, you have encryption. And I'm not going to go through this whole thing, but if you chop off the half, where it says SRES and goes to the right, those about halfway down, that's the authentication portion of encryption on a GSM network. And the protocol is pretty much like HTTP digest authentication. You both have a shared secret, which is K of I, and that's, you generate a random number based on that shared secret, and you send the challenge out, and it calculates a value based on that challenge and your shared secret, and it sends a response back, and you compare the responses, and okay, yes, you are who I think you are. We both have the same shared secret. Did anyone follow the Gemalto hack that was announced with the NSA and the UK? They hacked into a SIM, the biggest SIM creator, and stole all the K of I, the keys. So with a K of I key and an IMSI, you can clone a SIM card. There's no other technical mechanism to differentiate the card. The K of I is the most sensitive piece of information in the card. So if the governments did manage to get a hold of IMSI and K of I pairs from that database, then they can clone and decrypt any traffic generated by that card anywhere in the world, and not even within radio range over even remote links. So super great. Anyway, the rest of that is setting up the encryption session keys and exchanging those. But it doesn't matter if you've leaked K of I and somebody else knows it, you're done. That's it. End of story. So that was all kind of passive. I did talk about that active attack of cloning. If you copy KFI and MZ in the SIM card, you can just completely imitate a handset. You can also kind of abuse the network. This is without doing much other than abusing the services that are available on the network. These are the available services on a network. Location update request, it's like a registration. Mobile originated call, it's replacing a call, receiving a call, sending an SMS, receiving an SMS. And then there's another one called emergency call. So when you dial the emergency number for your country on your phone, it doesn't actually send a 911 to the switch, to the tower. It sends a special service request called emergency call. And that service request, the network looks at it, and if it's full of other traffic, it can drop other calls, drop other channels so that it can process the emergency call. And the emergency call also works without a valid SIM in your handset, without an active account on the network. So what some people did in Germany is they bought a bunch of used cell phones, powered them up, put them in a duffel bag, and right before they went to go rob a place, they dialed the emergency number on each of the handsets and set up 35 channels of voice, which saturated the towers, and then just went and robbed the place. And nobody can call 911 because they're all emergency calls. There's no priority. I mean, there's no way to judge if one emergency call is more important than the other one, so they just saturated the tower. And now they had to change that law in Germany where you actually have to have a valid SIM, a valid subscription on the network to make a call. So that doesn't require any equipment. Fuzzing the network would require some equipment. You'd have to have some sort of baseband access inside the phone. But you're not going to get very far. This is the core network. This is GSM's core network. All those boxes are different logical entities. Some of them run on the same hardware. Some of them run across links. Each of the links is a different proprietary protocol as well. So you're only going to get into maybe the BSC, which is the base station controller. You'll get in, from your handset into the base station, and maybe across to the base station controller, and then after that, you're crossing so many protocols that fuzzing doesn't do much. So it's much more interesting if you can create a fake base station, because the handsets implicitly trust the network that they're attached to. There's no way for you to authenticate the network. And there's even more meta information that you can ask in the standard. You can say, tell me what kind of hardware you're on, tell me your encryption capabilities, tell me the last registered network you were on, and what your TIMSI was for that last network. So, we see this when I'm, the company's in San Francisco, and when I'm on site in San Francisco, we have a logger. We have a license and everything. When you have a logger, and you can see people who were last registered to like China Mobile and have still not yet gotten service in the United States. They get off near the train station right near the office, and they still have not gotten service, and you see that, boom, they're trying to get service on our tower, and we reject them. And so you can see those sorts of things. That's information that might be interesting if you had one of these systems near an airport in Iran, and you see someone who was last registered to a network in Washington, D.C., and now they're trying to register to a network here. That kind of meta information that leaks out is a lot more sensitive than you might think. So the whole goal of having the rogue base station is to have an IMSI catcher, something that accepts all traffic. It's like having a captive portal, something like having a captive portal, or more like having a completely open access point that people can just join. The only difference is people don't know they're joining it. So you just impersonate the cellular ID of the network that's in the area, and if your signal is stronger than the one that is in the area, they'll jump to it. The handsets, you can't force a decision. You can only make something attractive to it. So you make your network more attractive than the other network, and it will jump on there. And it trusts you. So there's, once they're on, they're on. So fuzzing the handset gets a lot more interesting, because the handset doesn't necessarily mean somebody's iPhone or, whatever. Parking meters, for example, use GPRS. A lot of Internet of Thingsy stuff still uses GPRS. the data connection over GSM because it doesn't take very much energy and can be active for a very, very long time. Or payment systems, they also use GPRS still for the same reasons, because the waiter can walk around for hours and hours and hours without recharging the battery because it's not a 3G modem, and they're still stuck on GPRS. Taxi meters, all that stuff. No authentication of the network at all. Zero. Doesn't ask a question. There's no way to add it to the system either. But what does a rogue base station look like? Now, this is not the purpose of the company that I work for, and that is why I'm leaving them out of any mention here, because we do real base stations. We actually build networks in the mountains in Mexico and on islands, and set them up on rich people's yachts or whatever. Anywhere you want a GSM network to connect to, we can build that, and much, much cheaper. So our networks look like this. We have OpenBTS. It's user space software written in C++, which I've just learned is super evil. Written in C++, attached to an SDR, running on an Atom board or a virtual machine on a rack, whatever. Doesn't matter. There's a few other services running that speak session initiation protocol and real-time protocol to handle signaling and media for the phone calls. And then SMQ and SIP-authserve are a couple little 100 kilobyte applications that we have that process authorization requests in a way that GSM understands. And then SMQ handles SMS messages and does store and forward and rescheduling and delivery, that kind of thing. But those are just super basic things. This all runs on a little tiny, we're putting together a firmware, and the firmware is it's 12 megabytes right now. So everything fits in about 12 megs. And then you connect it over IP to, the interwebs, wherever you want to go. And if you start writing patches to OpenBTS, I'm sure you could do all sorts of fun stuff. For example, you can look inside the demodulated GSM frames right from Wireshark. We have something called GSM tap integrated in there, and it will take the GSM frames being exchanged over the air interface, frame them into something that Wireshark can understand, and you see these GSM tap frames show up. So at the top of that, there's two SIP exchanges, and these are for authorization. A handset is requesting the network. You see some SIP traffic come in being generated from the network saying, oh, I need to authorize. You need to, I'm going to challenge you with this number, send back a response. And the GSM tap frames underneath it are that request going out over the radio, the response coming in over the radio, and coming back down to SIP further off the screen. So in that little exchange, that would be a chance to fuzz. You can change some fields in there or add a couple of errors in and see what happens. As I was preparing this, someone put this on Twitter, which is super scary. Someone is writing a OpenBTS plugin for Metasploit, which is just a bad idea. Really, really bad idea. So I'm sure we're going to have a whole bunch of bad press on that. But it's not out yet. I guess when it comes out, there'll be all sorts of fun things like reverse GTP access into the phone. GTP is the protocol that runs the IP connection into the phone. So I don't know what's going to happen when that comes out, but whatever, yeah. Lots of fun. I'm sure there'll be a lot of questions. Needless to say, you have full access to layer 1, 2, and 3. You can do whatever you want in there. And so you can abuse protocols. You can do things like malformed or magic SMS. If you've ever used FaceTime, FaceTime registers itself over SMS. Same way with BlackBerry Messenger. They send out these magic SMSs out to some random number across the telephone network. And that's how they register your handset. That's how they do something similar to two-factor authentication. So they can send something over IP and then send something over SMS and coordinate those two. There's also silent SMS. There's like 5 layers to SMS, and you can flip a flag that says don't display to user. You can push out OTA updates, configuration changes, do all sorts of fun things with SMS. It's super, it's not real possible to secure unless you have a custom baseband on your phone. This is the worst one to me. Silent call is a real thing, and you can do it. It has been done, I guess, not with our stuff, but there's research on it, and you can manipulate the layer 3 interactions and state machine in GSM to set up a call to a phone, have it be answered, but never indicate on the handset. So that means your microphone is active on your handset, you're in an active call, so your voice is being transmitted somewhere. Sorry. And it also means that there's an active radio connection to your phone in your pocket. Most of the time, your phone's in your pocket. It's not in an active radio session with a tower, so there's no meta information flowing back and forth about how weak or strong the signal is. There's actually no way to tell how many phones are camped to a tower. But if you set up a silent call, you can. You can tell that this phone is active, it's on this tower, it has this signal strength, it's moving at this speed. You can tell all sorts of things from it. You can also do something called RRLP, Radio Resource Location Protocol. You can send a request to the phone that says, if you have a GPS sensor in you, could you send me your exact latitude and longitude right now? And as soon as it has a fix, it will send it to the network because it trusts the network. Why would it's impossible that anyone would have a multi-million-dollar network, or, well, like $400. Slight difference in the thinking required. So these are bad things. This should be on the way out, though, right? GSM, super old, showed up 30 years ago. We have UMTS, 3G. We have all the extensions to UMTS that increase data speeds. That's being rolled out everywhere. Long-term evolution, going out everywhere. 4G. Everyone's upping their data plan and their shared family junk so that you can look at videos on it. And both of those have mutual authentication. So they won't jump on a network that they can't authenticate cryptographically in the SIM card. So the SIM card has to have keying information about the network. There has to be a real 100% cryptographic exchange in both directions for it to jump on the network. Great, wonderful. But they reverse to GSM if they need to. So if you make GSM more attractive to the handset and you make UMTS less attractive to the handset, they will jump back to 2G and they'll jump back to the authentication methods used by GSM. This is also the killer. When they standardized GSM, they had a secure indicator in the handset. It was defined. In the display of the handset, there's going to be a lock if it's a secure connection. But then they made it optional when they were almost done. So let's take a drink. So they made this optional. This is 3GPP land. This isn't the IETF. But the IETF equivalent of this is should instead of must. So should or can or may. They basically made it optional, so there was no way to tell if your connection is secure or not. But they thought it would cause user confusion and mistrust or something. So now, that is what we're paying for. There's no way to tell if your handset is actually connected to the network that you say it is, and if it's secure or anything. Wonderful. SS7. Who knows what SS7 is? Hey, one hand. SS7. It's Signaling System 7. So can you guess how many signaling systems they had before SS7? 6 of them, yeah. So SS6 was the last one, I think is the last one, where you could take a tape recorder and put it up to the handset of a payphone and play back some tones. And the signaling would go through the media path and you could trigger interactions on the switch and things like that. So the big step forward with SS7 is they separated signaling and media. Wahoo, at long last. And it's actually just a platform. It's a digital platform like like the internet. It's a big global network. And telephony is just an application that runs on top of this network. It doesn't use IP. It uses global titles and point codes and all this fun stuff. I'm not going to talk about that because I don't understand it. SS7 enforces its security through bureaucracy. Great model. Basically, they figured if you were doing anything illegal, if you're two bordering countries or two bordering operators, and someone's going to roam onto your network, this is the core network that connects all the individual networks. This is how roaming happens. If you were going to do something malicious with roaming, well, you would never want to because this is how you make money. And if the other operator figures out that you're doing something bad, they'll just ban you from accessing the core network. Well, that's great. But then they made a differentiation on the SMSC, which is the SMS Service Center, the thing that sends and receives text messages on that core network. So it has access to the core network. It is a 100% real member of the core network, but it can be operated by much smaller players. You don't have to be a government. You don't have to be AT&T to have these. So you can get access to an SMSC pretty easily. And on the gray market, you can get access to SMSCs that do funny things for you, like geolocate somebody by their phone number. Before, you actually had to know the IMSI. You had to know the secret number that's deep inside the SIM card. Now, if you have somebody's business card, you can tell where they're at. You can tell within a tower distance of where they've been over the last months. You can track them over time. You can send requests through the SMSC every 15 minutes or every hour for 6 months. And you can start to figure out where they go and what they do and who they talk to and who they're with. So that's horrible. But it's, not restricted at the network level. You can also toggle toggle account options on the phone remotely. Well, that's not a big deal, except for like call forwarding. That's kind of a doozy. You can just say, don't actually make this phone call ring this other phone, and we'll intercept all the calls that way. So we don't have to be anywhere near the phone to intercept the calls. Now we can sit in a lab with an SMSC contract and do all this sort of stuff. I guess the creepiest part about this is people like to say, well, shut down all these cheap SMSC operators. But some governments may or may not be, doing core network shenanigans all the time. It doesn't matter. It's not these little, temporary SMSC operators that do slightly nefarious things. There are entire governments that have access. Most governments have access to the SS7 network almost exclusively in their country. So they can do whatever they want in there, and there is no inherent security inside the core network that runs all of the global communications at all. There's just nothing there. And roaming authentication in SS7 is a joke. So let me show a super lovely slide. There's 3 circles, and the stuff that's being exchanged in the middle is a bit custom. That's what we do. It's a SIP to SS7 or SIP to SS7 map gateway that we have operating. But the ladders on the left and the right are 100% how it would be in a core network. So what you have at the very top on the left is a handset that is doing a location update request. It says, I want to join your network. And we send that on, and we request authorization information from their home network because they're not our subscriber. It's somebody coming into our network from another country or whatever. So we ask for their encryption, their authentication keys. And their home server sends us back a few tuples of them, so we don't have to ask every time. And since we don't have to ask every time, there is no state connection between the top and the bottom of what's happening on the right. And what's happening on the right happens after we ask the phone for their authorization keys. We challenge them with a shared secret. We do all that fun stuff, and then we compare the result and send it back to their home network and say, oh yeah, it's them. We asked the phone. But there is no connection between the top and the bottom at the protocol level. So we could just lie. We could just say, yep, this person just joined my network, and all their traffic goes here, and route it somewhere else. You don't have to, you don't even have to ask for the authentication keys. There's nothing in their network that would say, oh, this is strange. They joined this network, and we've never sent them keys. So you can do that kind of stuff. And then, of course, the cipher mode on the end side, the final link to the handset on the air interface is completely optional. So we don't even have to turn on encryption if we don't want to. We can authenticate the keys, or authenticate the phone without ever having asked for keys, and then leave it unencrypted if we want to. All sorts of fun stuff. So this is the actual solution. If you have a phone in your pocket, that's it. If you don't want anyone to track you, follow you, figure out what you're doing, that's about it. Take out the battery, shut off all the radios. If the radios are on, it's findable, it's discoverable, it's manipulable, you can send a text to it, whatever. So I am 18 minutes short, which means I have time for questions if anyone has questions. I hope someone has questions. These are the references, by the way. That visualizer thing is online. That's for the software. And then those are a couple of groups. Yeah.
In doing your research, have you found any phones that are actually still connected to the network, or they're actually made set? That seems like a software set.
Oh, yeah. The question is if there's any misbehaving phones that still have their radios on with airplane mode. Not that I know of. Certainly could be. I mean, the battery out is the more secure one. There are phones that are coming out now with baseband modifications that have like a baseband firewall in them, and it'll say, my network ID changed, and it changed again, and it changed again. Like, this is very strange. There's a lot of weird activity going on the baseband level. So there's some things out there like that. Oh, if you actually need a full SDR to do the cell phone network, or if you can get by with a phone and a modem, there's a cool project from these guys called Osmocom. Osmocom also has they're a competitor to OpenBTS. They have another stack. They have a lot of core network stuff, but they also have a baseband project, and they reverse engineered a Motorola phone, I think. They reverse engineered the baseband of a Motorola phone, and they can get it to be a base station. So you only need this specific Motorola phone and reflash the firmware, and you have a completely mobile base station. I think it can handle one voice call, or maybe it can only do like signaling, but there it is. It's it's a little cell phone. What? No, well, in that case, you don't need an SDR, but that's a corner case. You still need if you want to do this, you need you need a radio. You need, probably, this is 400, so it's about the cheapest one to get. The Hack RF, a lot of people were interested in that because it's cheaper, but it's only half duplex, so it doesn't work. Oh, if CDMA works the same as GSM for security, I wish I knew. I don't know. I really don't know. There's probably a short answer from somebody who knows, and they'll say, yeah, kinda, or not. But I don't know. But, sorry.
For a malicious base station,
If femtocells work as malicious base stations, they do, but in a different way. So femtocells are not independent of the core network. They're a trusted member of the core network. And usually trusted members of the core network are housed in locked buildings with chain link, angle fences over the top of them in, next to highways or whatever. And femtocells sit on kitchen counters so that you can have better access to AT&T while you're inside your concrete apartment. So they've stuck a trusted entity in the core network inside a residential home, and some of these femtocells have serial ports in them, and some of them were not very well secured, and they've been reverse engineering the femtocells themselves to fuzz the core network in a completely trusted manner. The core network trusts the femtocell. So it tunnels back to the core network over your internet connection. And now they can fuzz those other entities that were further back in that diagram. They can fuzz those entities because it's a trusted base station. But as far as reprogramming a femtocell to do anything you want it to on the air interface side, can't really. Not that I know of. Okay, well, I'll be around if anybody else has questions. I was just going to mention the bottom here, this Bay Area Cyber Spectrum group. These guys just started out. They're really interesting. So if you want to just watch videos, not about cellular stuff. I don't think they've had anybody talk about cell stuff. If you want to just learn about people using SDRs and really crazy things, watch those videos. There's a guy who had a signal coming into his SDR and couldn't figure out what it was. He figured out it was dual phase shift keying, which means you have like these two circles that are kind of rotating on your screen when you lock onto the signal. But then he also saw that it was rotating around each other, so they were rotating this way and also doing this. And then they figured out that it's an old satellite that went out of whack in orbit, and it is spiraling itself physically around like the North Pole. And that was what he was seeing over the horizon as he was aiming at something else. And so he actually participated in there's an article maybe 2 months ago about them reviving this satellite that took all the Arctic imagery from the 60s. That's that guy. They reverse engineered the protocol that was used to control the satellite and get the telemetry data out of it. And they did all this with this. He works for this company, works for Edis. So that's the kind of stuff they do. It's pretty cool. All right, thank you.